Well, hey, everybody. Welcome again to Astronomy Daily Live. You can call me Cosmic, and it is 2 hours UTC. And every single day, more or less every single day, at this time on this YouTube channel, we gather together. I sort of create a virtual space here, and we gather together an ever-growing group of friends, sort of like-minded, that share a passion for the science of astronomy. So welcome, come on in, join the circle of friends, this virtual porch, right, where we're gathering together with our consumables of choice. So I have a little bit of coffee left here. That's about it for that. And of course I have the hydrogen hydroxide again. And Bobby has just reappeared on the panel. Hey there, Bobby. What's happening?
Nothing much. You?
Everything's good. Everything's good. So yeah, hope everybody had a nice Equinox day. Past 24 hours was the first 24 hours this side of well, fall in the north and spring in the south. And you know, there was one thing that I forgot to mention yesterday about the Equinox that is very, very cool. So Atta's in the chat. Hey there, Atta. Nice to see you. Cloudy again. Yeah, it's clear here. Big bright moon. Big bright.
Hey, Atta.
So cool. Nice to see you in the chat. Yeah, the one thing that I didn't mention, probably one of the coolest things, is that at the equinox, right, at those two times, if you are standing either on the North Pole or the South Pole of the Earth, in a 24-hour period, the sun will go completely around you. It'll go around the entire horizon once, right? So like right now, the North Pole and the South Pole are in a perpetual sunset. So, and that's got to be pretty awesome, right? Pretty awesome. Hey there, Uncle Bill. Nice to see you in the chat as well.
Yo, Uncle Bill.
So yeah, that's yeah, you know, those kinds of things aren't you know, at least I don't hear about those kinds of things, right? You always hear about the midnight sun, but as far as I know, I mean, I've never heard anybody else mention the fact that on the equinoxes you get this 24-hour sunset, and it actually lasts, right? I mean, more or less, you know, for several days, right? I mean, the equinox is when it'll sort of be maximum. Hey there, unicorn potato. Nice.
Hey, I haven't seen you for a little while.
Yeah, hope all is well. All is well. So yeah, so if you're standing on the North Pole or the South Pole this time of year, right, what you'll see is the sun just go all the way around you, right on the horizon. It's like a perpetual sunset for several days, right? For several days. until you know our orbit changes a little bit, and that angle isn't quite the same, then we'll start having a little bit more dark and a little bit more light, depending on which hemisphere.
Yeah,
you're
and
on.
before you continue, I'm not sure if Tagore Raptor is going to be here, but this is a photo of a professional wrestler who just retired yesterday from his last match. He did want to take on me, but but we took a nice photo.
Yeah, that's very cool. That's a nice shot. That's a very,
So
very cool
I
shot.
know Tagore Raptor is a great wrestling fan. I'm just not sure if everybody else is a great wrestling fan too. I know Atalanta knows that I love wrestling.
Bobby is totally into wrestling. Yeah, that's very cool. That's very cool. It's nice to have, lots of interests if you can get away with it. For sure, for sure. So yeah, I don't know if mute that. So I posted another video, sort of call it Orbital Ballet. I just took the Earth and 3 random asteroids, and over a 10-year period, looked at the positions of them relative to the sun, and did another sort of barycenter, geometrical center calculation based on those 4 objects, and then made a little movie into it to sort of show off those motions, that is. So let me see if I can. Yeah, here it is. So
Isn't that video you just uploaded?
yeah. So a little bit of artistic license here, but not very much. So this inner dot here, that is the Earth rotating around the sun. Now, the reason why it's going in sort of a weird path is because part of the artistic license that I've taken is that I'm rotating this whole scene, right? So yeah, so the motions of these objects are going to look a little weird. So, but anyway, this inner one is the Earth, and then these 3 others are these 3 asteroids. I just randomly chose 3 asteroids. And so,
what's that line that is tracing around?
Yeah, so that line is just the geometrical center. So if you take all the x positions and average them, then I get the x position of that line. And if I do exactly the same thing for all the y positions and all the z positions, it's just the average x, y, and z position. And then again, colorized a little bit. But yeah, it's sort of showing, relationships, and yeah, it's just a little fun thing.
And that's the onlyest video that you did, or you made some more?
This is the only one that I posted recently. Yeah. This is, the result of a lot of experimentation and a lot of messing around and all of that. But so yeah, it's because I'm rotating the point of view, the paths of these objects are are, you know, definitely, you know, not what you would expect. But yeah, that's just because I'm rotating things around a little bit. Anyways, that's just a little fun. Just a little bit of fun. Relaxing today and doing some astro art.
She had never seen anyone present present astronomical data of any kind in this manner.
Yeah, it's you know, um, I think it's pretty interesting. I really don't know what I think of it yet, and I've been doing it for uh, many years now, and I still don't know really what to make of it. I mean, I like it, you know. I mean, I hang it on the wall. It wins awards. Uh, these prints get sold from time to time. So so yeah, I mean, I think they're interesting, but yeah, I don't know. I think there's a lot more that I could do. Um, but yeah, don't know. Don't know. It is interesting. It's an interesting way to represent really any kind of data. It doesn't have to necessarily be astronomical data. That's just the data that I'm sort of used to, right? But I mean, it could actually be um, this kind of art could be created with any kind of data, anything, doesn't matter, right? I mean, I've taken telemetry from spacecraft, right? Temperatures and um, gimbal positions and baud rates and all that kind of stuff, and you know, made the same kind of art. So yeah, there's lots of possibilities there, and it's just it's a matter of exploring a little bit uh, and seeing what's possible. And at least at least in my case, it really helps to be able to you know, do some basic programming so I can manipulate those values um, to sort of make them more acceptable to the plotting program that I use. So yeah, it's just fun. It's fun, and always looking for something interesting. So I don't think that that video is necessarily like incredibly wow, but I think it's moderately interesting. So if it's interesting, I'll post them. But otherwise, yeah, it's just there's a lot of experimentation. It's a lot like composition, right? With music, right? I mean, you go through a lot. Well, usually at least, you go through a lot of you know, trying this and trying that until you get the kind of sound that you actually want. And it's the same kind of thing with what I'm doing. Just a lot of messing around and
Welcome, Chuck Nagalum.
just having fun. We got, hey there, Chuck. Nice to see you in the chat as well. Live long and prosper. I can actually do that
Live long and prosper.
with both hands.
Yeah.
Yeah. So very cool. Yeah. Let's see. Cheers. So yeah, really nice Equinox. Very nice and peaceful. And yep, that was really fun. It was nice to be sort of outside instead of cooped up in here. So that was very cool.
especially being in like a little closed area or like a city or something.
Yeah, yeah. So yeah. Special time is the equinox, when at the poles at least you're in perpetual sunset. So that must be an interesting sight. Like to see some pictures of that at some point. Could be interesting. Could definitely be interesting. So, this is Astronomy Daily Live, and what we do here is we think and talk all things astronomical. And there's always so much. It's absolutely amazing. This universe of ours, full of incredible things, and so much to think about, and to contemplate. So we were looking at the constellation of Pegasus the other day, and it's such a huge constellation that I sort of wanted to give it its due time. To sort of look at a few of the objects that are um, uh, in this constellation, and yeah, see if there's anything interesting. Right, see if there are any particularly neat objects, or some star is doing something in sort of a weird way. We really like the unusual things, and the interesting thing about that, of course, is that if you look hard enough, pretty much everything has its little quirk, right? It's the astronomers, we like to try to categorize things and say, that this is, these are spiral galaxies, right? And these are um, elliptical galaxies, and all over the place, right? And it's hard to categorize things that way when you start looking at the details, right? There's always, I mean, each thing is pretty unique, and it might fall into sort of a category, but not always. Not always. So cheers. So So I had pulled out my Burnham's Celestial Handbook, the messy one here, and we were going through Pegasus
And welcome,
in this
Tarbert.
guy. Hey there, Tarbert. Nice to see you in the chat. So yeah, I think we were looking at NGC 7217 with Hubble the other day. So that was pretty interesting. There were some, I think there's some variable stars. Yeah. Pegasi. Pegasi. Let's see what it says here. Okay, so this is a eclipsing binary. So this is a binary star system where it just so happens that the secondary star, as it orbits the primary star, from our point of view, the secondary star passes in front of the primary star. And so, yeah, that makes it pretty interesting. Let's say here about that. Let's see. Let's see if Sinbad has anything to say about Pegasi. Is what we do here on Astronomy Daily Live is just sort of follow.
Did you ever take a look at that Morse code text?
Nope, haven't looked at that one yet. I need to. Thank you for the reminder, though. So let's go over here, and we're going to go Sinbad. And you Pegasi. You Pega. Whoa, bad typing guy. Pegasi. I think that might get us there. Yeah, there we go. Eclipsing binary. So there are different kinds of eclipsing binaries, and they all have sort of a prototypical one, which in this case is W Ursa Majoris. So that was probably the first one of this type. And so if they find another eclipsing binary star that has the same characteristics, then it's that type, right? So that's what that's all about. So here's the right ascension declination. Cool. Proper motions, milliarc seconds per year. So it's moving west and south. Okay. It's also moving towards us at about 28.5 kilometers per second. Let's see. And pretty faint, right? 8th, 9th, 10th magnitude or so. They're different magnitudes because we are looking at these at different wavelengths. And depending on characteristics of the star and or stars, those brightnesses at different wavelengths are going to vary. So that's why there's a little bit of variation here. Let's see, a bunch of different names. It's kind of interesting. Oh, okay, yeah, right. Gaia Data Release 1 hasn't named that. Gaia Data Release 2 hasn't named that. So that's kind of interesting. It is, yeah, pretty cool. So pretty well.
Again?
I'm sorry?
Have you seen the galaxy again? Or that's a star?
This is the star Pegasi.
Oh, okay.
Yeah. It's a eclipsing binary star. I'd like to see some light curves is what I'd like to see. Let's see, they've got a distance measurement here, 137 parsecs. So what, that's about 400 light years. Pretty good agreement with the velocities, proper motion, sort of. Parallax looks pretty good agreement there. I don't remember what these other things are. Pretty cool. Let's see if we can find UPEG. Photoelectric photometry of eclipsing contact binaries. Ooh, cool. Well, let's take a look at that because that's definitely going to hopefully give us a light curve. Well, let's see. All right. Photoelectric photometry of eclipsing contact binaries, Pegasi. Yay. So this was 2001. I think it looks like it was published in 2002. So we're just sort of interested in, oh, here's some characteristics. It's got a hip number. Velocity. Spectral type is a G2-5, which is, wow, that's I think that's what our sun is. I think our sun is a G2-5. So that's kind of interesting. It's a contact binary, though, huh? So that means that the two stars are actually in physical contact with one another. That's pretty nice. There's a lot of those, though. You know, it turns out that there are quite a few. Does this say something about it? The variability of UPEG was discovered in 1894. Later observations revealed that UPEG is a short period eclipsing binary. Partial eclipses. The most massive component is the cooler one, so the system is of the W subtype. Frequent photoelectric photometry shows significant asymmetries in its light curve. These changes can be relatively well interpreted by the development and migration of spotted regions on the cooler and more massive component. So they've taken spectra. Okay. They don't say what the two different spectral types of the two different stars are, though. They just give one. The period changes in the system were studied by these folks who interpreted the long period change as a light time effect caused by a third body. Okay. So there's the observations that they did. And let's see, I'll back out a little bit here. Light curve extrema. Let's see some light curves. Okay, so here are the new times of the primary and secondary minima. Here we go. So there's UPEG, and let's see what the so the photometric BV light curves and B minus V color index. Oh, I got you. Yeah. Okay. So yeah. Here's the B filter light curve, and here's the V filter light curve. So you can see that B, that it's, ooh, okay. Wow, this is a little confusing, because this scale, photometric BV light curves and B minus V color index. Yeah, these are kind of confusing units over here. They're showing delta B, which is usually like a change or a difference in B. That I'm not quite sure what that means. And why does this go from 0 to 0.7 and this goes from 0.4 to 1? Okay, here. Oh, I got you. Here's 0.4. Oh, all right. So yeah, they're not quite sure why this scale is sort of the wrong way, right? It's going up as you're coming down. Not quite sure, but I'm pretty sure that uh, that these are the lows and these are the highs, right? As opposed to the other way around. I don't know. And then that's kind of neat. This is just the difference between B and V, right? So you're seeing how the color changes as they orbit. That's kind of neat. That's kind of cool. Okay, and here are the dates. Okay, so those aren't all the same. Ah, I got you. Yeah. Yeah, cool. Okay. Pretty sweet. Lots of, well, not really a lot of structure, but pretty complete light curves for sure. Don't really know what's going on here, right? But that might be part of the variability. You know, the how 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 this variability is changing, right? One time it's like this, the next time it's like that. So yeah, there's some interesting stuff going on there for sure. That's pretty cool though. Let's see if they've got anything else on UPEG. So yeah, the orbital period of the system decreased over the whole time interval of the observations. The rate of the decrease, however, is variable. Explained by the conservative mass transfer. Okay. Okay. Not quite sure. The photographic, photoelectric, CCD, and spectroscopic times of the primary and secondary minima. Huh, okay. A couple of references there. Just a couple. Excuse you.
Excuse me.
So what's this? O minus C diagram of all photographic CCD and photoelectric minima. Yeah, so kind of interesting. Even the minima are changing. So, huh. Pretty cool. Let's see if there's anything else on, specifically on Pegasi. Okay, what's this? Separate clean solutions. Okay, so yeah, they've as all good astronomers do, they've got their models, right? And so they can fill their models with things, tweak parameters, and come up with light curves that, yeah, might be sort of similar to the data. You know, obviously, here's the actual data, right? These are the measurements, and then these smoother lines, either the solid or the dashed, is the result of some kind of model. But pretty good agreement. Pretty good agreement. So UPEG in 2000, UPEG in 2001. Things don't really seem to change much. Looks about the same. Down to 0.6. 0.6, yeah. Anything else here? Photometric elements and their standard errors. So yeah, they're looking at the inclination of the orbit. They're trying to get, other orbital parameters there, of which I'm not too familiar, unfortunately. Can't know everything. So yeah, I'm not quite sure what A is. R is the radius of, like, R1 and R2 are likely to be, the radius of component 1 and the radius of component 2 as a ratio to the size of our suns. See, so that's an R sun. So the primary is a little bit bigger, the secondary is a little bit smaller in both radius and mass and density. It looks like they're sort of showing that the density of the second component is actually higher than that of the first. That's kind of interesting. 132 parsecs away, they say. Kind of cool. So that's view peg. Let's see. I should probably check the chat while I'm switching back. No activity in the chat. No shenanigans whatsoever. Cool. So let's see what else we have here. I'm going back to Burnham's, looking around. Pegasus. So yeah, NGC 7814 is probably worth a look, and Stephan's Quintet, for sure. Let's look at 7814. That Burnham's has it looking like that. This guy. But I wonder if HST has looked at this guy. And we can look at Sinbad too. Let's see, Sinbad. Let's do Sinbad first, and I'll switch my screens here. NGC 7814. And we'll switch my screens. Share my screen, that is. There we go. Galaxy in group of galaxies. That's kind of funny. Oh, so this has the Sloan Digital Sky Survey image. Which, wow, that's pretty spectacular looking. So in the infrared, JH and K, right? It's a pretty bright galaxy, right? Seventh, eighth magnitude. But in the visible, like in B, U, and G, and R, look at that, it's pretty faint. But it leans towards being brighter in the red. And if this is sort of representative of the color, then yeah, that is a pretty red-looking galaxy, especially with this amazing dark band going right through it. Pretty nifty. We should see if HST has got it. Very unlikely, but let's look anyway. NGC 7814. All images, all spectra, everything else. Ooh, cool. We're doing really well with this lately. ACS, I always forget what ACS stands for. That's pretty sweet, though. A little overexposed, but pretty spectacular. I saw a bunch of other galaxies up here.
And don't forget about going to the Wise.
Yeah, we'll see. We'll see what Wise says about this. Look at all these guys back here. These little galaxies way in the background. We got this big monster. Ooh, look at these. Lots of galaxies here. Lots of galaxies. And of course, this big guy, 7814. So that was taken at 5920 angstroms. They've also got one at 8044 angstroms, more towards the red, very red. Probably show off a lot of dust. Yep. Pretty spectacular dust lane here. Pretty dark, right? I mean, everything white on this image is actually dark, right? This is a reversed image. And everything dark is actually bright. Sometimes it's nice to look at things this way because the fainter things tend to sort of pop out a little bit more. But it's always nice to see this in sort of true color, or not true color, but bright things actually being white. So let's just save this.
You still never did your package updates yet on your package manager on your Fedora?
No, I haven't yet. 24. Let's take a look here. We're going to open it with GIMP. And we'll just do a quick...
You're going to invert it, right?
Yeah, I'm just going to invert it. Make it a little bit bigger. There we go. So yeah, pretty amazing little object here for sure. That's nice little galaxies in the background. There's kind of a funny looking thing there. I don't quite know what that is. Yeah, lots of galaxies in the background for sure. Yeah, pretty nice. Pretty nice. So most likely this is some kind of a spiral galaxy. Most spiral galaxies do have these dark lanes. Quite a few references. That's kind of cool. Get past all the references here. Quite a few distances, so pretty good agreement, maybe around 14 or 15 million parsecs. So that's actually pretty close. A million parsecs is 3.26 million light years. times, let's go 15. Yeah, see, so that's only like 48.9 million light years away. So really, actually, pretty close. Pretty close, in the neighborhood. In the neighborhood. Yep. Let's see. 814. Let's look at the papers and see. So MOND is a modified Newtonian model for gravity. It's a different kind of gravity model. The tale of two galaxies, light and mass, in NGC 891 and NGC 7814. So 891 is also a edge-on galaxy. Actually, it looks pretty similar to 7814, as I recall. Light and mass. The globular cluster system. So they've actually identified globular clusters in this galaxy. And that's probably going to be these, at least some of these little guys. Some of them, at least. Let's see. Wide field photometric survey. We're now attempting to automatically create some PDF from the article source. Results of wide field photometric study of the globular cluster system of the Edge-on SAB spiral NGC 7814. Let's see, they used the WIN telescope up on Kitt Peak. Globular cluster candidates. Let's see. The initial results from our survey suggest that the globular cluster systems of typical ellipticals can be accounted for by the merger of two or more spirals. Globular clusters in other galaxies. Very cool. Data analysis. Yeah, so they tried to fit and then remove the light from the galaxy itself. That's pretty hard to do. Yeah, lots of galaxies, lots of stars. Here's results. Looks like all of their pictures and diagrams and everything are at the end. So I've got to page through this a little bit. Summary. So our data provide radio coverage of NGC 7814's globular cluster system to 7 arc minutes from the center. Has a total population of approximately 200. Cool. Many fewer globular clusters than previously thought. Cool. Let's see if we've got any interesting pictures here. I like pictures. Okay, that's just showing some instrumentation stuff. 398 detected objects. That's an interesting, sort of a Hertzsprung-Russell diagram. It's a color-color diagram. So they've taken the photometric magnitude of this object in three different wavelengths, B, V, and R. And then they've simply subtracted V from B and R from V, and then plot the result. And try to fit various models to it. Kind of complicated. So there's a color magnitude diagram. So number of targets per radial distance from the center. I was hoping they'd have some pictures. That's not a very useful plot. Oh, no, that's a table. Okay. Oh, that's it. Yeah. Okay. Well, they don't really show a picture identifying, but yeah, they've identified over 200. That's pretty good. Not too bad for 49 million light years away. Bulge and warp, NGC 7814. Looking through the dust, the Edge-on Galaxy 7814 in the near infrared. Okay, so here's an earlier paper detecting globular clusters. Surface photometry of three early type Edge-on spiral galaxies. Dynamics of galactic bulges. 4594, I don't recognize that. Bulge of the lenticular galaxy. So back in 1985, they were thinking that this was a lenticular galaxy. (1982). Okay, that's about it. That's about it. Well, yeah, what an amazing galaxy for sure. And
now, if we was able to go into a galaxy, what would we actually be seeing?
Just a bunch of stars. That's it. That's all you would really see.
I thought like you might be able to see some planets as well.
Well, it depends. It depends on where you are, but you know, there's a lot of space in between things, and so you know things look relatively close to one another because they're just so far away, right? But in truth, you know, each of the stars in that galaxy are, you know, most likely tens of light years apart from one another. So running into a planet, sort of unlikely. All right, you guys. Well, you know what? I think I'm going to get out of here a little bit early today. So hope everybody has a great evening, a great day, and let's do this again. Let's do it. Let's do it in about 23 hours. How about that? Yeah. Let's do some more astronomy, and for the time being, take care, everybody, and I will see you on one spin. All right. Take care, everybody. Bye.